Okay, so good morning, good afternoon, whatever time, evening you are watching this. Today we are going to be watching, or you will be watching a video, I am making said video, a video on related rates. And so this is topic 2.6 that we will be working through. And without further ado, 2.6 guided notes. Objectives for this lesson are to find a related rate and use related rates to solve real-world problems. Homework is problem set 2.6 posted on WebAssign, and the lecture will be linked as soon as it's finished. So part 1, finding related rates. In this section of chapter 2, we are going to move implicit differentiation out of the hood. So we're moving out of X's neighborhood, and we are going to move into T's neighborhood and solve problems that involve the rates of change of two or more related variables that are changing with respect to time, hence T's neighborhood. So previously, X was our independent variable. Now T is our independent variable. And so we are in T's neighborhood. And if we're not a T, then that means we need to prime ourselves. But that's getting ahead of things. Think, for instance, of water draining out of a conical tank. The volume, the radius, and the height of the water level are all functions of time. So these variables are all changing with respect to time. For instance, the volume at the starting time is going to be different than the volume 2 seconds later because water is draining out, right? So our volume is decreasing with respect to time. Further, we know that these variables are all related by the following equation. Volume equals volume equals pi over 3 r squared h, okay? So if we differentiate with this equation with respect to time, we can obtain the related rates equation. So let's do that. So we have V equals pi over 3 r squared h. And to indicate that we are taking a derivative with respect to time, we're going to write the whole thing in brackets and put d over dt on the outside. So remember, the same dy over dx is the same thing as y prime, okay? So d whatever over dt is the same thing as whatever prime, okay? So let's think about this. We're going to have dv over dt when we take the derivative, because again, the derivative of volume, or just v, some variable, the derivative of a variable is 1. But since we are not in a t, a v is not a t, then we need to prime ourselves. So, example, dv over dt is the same thing as v prime. So we can write it either way. I'll write it the equivalent way on the bottom. Equals. All right, so now we're taking our derivative. I'm going to use the constant multiple rule, and I'm going to pull out that pi over 3 because students forget this, but pi is a constant. So I'm going to pull out my constant, and then I'm going to use the product rule to find the derivative of r squared h. So first, r squared times the derivative of my second. The derivative of h is 1, but I'm an h, not a t, and so I need to prime myself. And I'm going to write that as dh over dt, or as h prime. So this could also be written as pi over 3 r squared h prime, first times the derivative of the second, plus second, which is an h, times the derivative of the first. The derivative of r squared is going to be 2r, but again, I'm an r, not a t, so I need to prime myself, dr over dt. So that could also be written as plus h times 2r times r prime. Okay, and so this down here, these two answers, which are equivalent, just depending on the way you like to do notation, are the related rate equation for volume. We've taken the derivative of the volume formula with respect to time. So keep that in your brain. That's important. So problem solving with related rates. Evaluating the derivative of a given function using all of our handy rules is fun and all. But solving related rates problems really gets at the heart of why we learn derivatives. Aside from me nerding out and saying that it's one of the founding pillars of calculus, which it totally is, but anyway. Think of inflating a balloon. As the balloon is blown up, there are many changes that are taking place, including changing radius, changing diameter, changing surface area, and changing volume. Again, same thing as with the tank draining water. As we blow up the balloon, we're going to have an increase in surface area. We're going to have an increase in volume. we're going to have an increase in the radius because the rate, or not the rate, because the volume of the balloon, all of those things are changing as time passes, as we inflate air into said balloon. Since we're dealing with the same balloon, we know that the rates of change must be related in some way, but the question is how. Some things we know that radius is related to diameter in the sense that radius is equal to diameter over 2, or diameter is equal to 2 times radius. We know that surface area is equal to 4 pi r squared and volume is equal to 4/3 pi r squared. So there are a bunch of different variables in these equations. Therefore, to find the rate of change of one variable, we need to differentiate the formula. So right there, that should be like ding, ding, ding in your head, because whenever we hear rate of change, we know derivative, we're dealing with a derivative, okay? So rate of change, derivative, that should send off a warning bell in your head. Further, since all these variables are changing with respect to time, time will be our independent variable, and we are going to enter T's neighborhood and implicitly differentiate our formulas and equations with respect to time. So, solving related rates problems. We're gonna go over the general guidelines, do a few examples, and then I will leave more examples for class time. You'll do more examples in the homework. Like, we are gonna do so many related rates problems. Just buckle up. Anyway, here's what you need to do to solve a related rates problem. And I know this makes it sound so easy and you're all gonna be like, it's not that easy, but it is. Just follow these habits. Draw a picture. Students hate this step and often skip it, but do it because it will help you. So draw a picture. Identify what information you are given in the problem. Identify what you are asked to find. Write the equation or equations that you will need. Differentiate said equation with respect to time. And since we're in T's neighborhood, that means that every variable that is not a T needs to prime itself. So basically every variable, unless you happen to have a T in your equation. And then solve, okay? So after that, we are going to do some practice problems. Okay, so let's do some examples. Air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. So let's go ahead and draw a balloon that is a sphere, and air is being, there's the little thing and like a string. Air is being pumped into the balloon, or maybe it wouldn't have a string yet if it was getting inflated, whatever, at a rate of 4.5 cubic feet cubed per minute. Find the rate of change of the radius when the radius is 2 feet. So step 1, picture, check. Step 2, I want to write down what is given. So I know that air is being pumped into the spherical balloon at a rate of 4.5 cubic feet per minute. So one thing you have to do for related rates problems is think about what the information given to you in the problem means and how you translate that into math. So in this case, it says air is being pumped into a spherical balloon. So that means that the volume, or the rate of change of the volume, or dV over dt, is equal to 4.5. And that's what's given to me, okay? Now, I want to talk about what I need to find. Okay, again, whenever you're asked to find or you're given something that uses the word rate of change, that's always going to be derivatives. So that's always going to be something over dt, d something over dt, depending on what variable it is. So, for example, air is being pumped in. That's dV over dt because it's the volume changing. They're asking us to find the rate of change, ding, 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 something over dt of the radius. So that's going to be dr over dt, the rate of change of the radius in terms of time, when at the moment that the radius is equal to 2 feet. So remember that up and down bar means evaluated at or at the time that, okay, so that's what I want to find. Finally, equation. My equation for the volume of a sphere is 4/3 pi r cubed, okay? And so these equations will be given to you, or you can look them up. I don't expect you to memorize a bunch of volume and surface area and whatever equations. So there's the equation for the volume of a sphere. I'm gonna put V equals because that's good form for equations, V equals. All right, so picture, check, given, check, find, check, equation, check. Now I'm going to differentiate my equation with respect to time. So I'm going to erase my writing right there, and I'm going to draw these nice little brackets and d over dt, indicating that I'm taking the derivative with respect to time. The derivative of v is going to be v prime, or dv over dt, is equal to 4/3 pi is all a constant. So people, students, whatever, tend to forget that pi is a number, but it is. So you can pull it out and use the constant multiple rule. So I'm going to have 4/3 pi out here times the derivative of r cubed, which is going to be 3r squared, but I'm not a t, so I'm going to also have to prime myself, so I'm going to have to multiply by r prime. And up here, I'm going to rewrite these v prime equals 4.5 and r prime when r equals 2. Equivalent ways, but now I can see that I can plug some stuff into my equation, right? So v prime I know is equal to 4.5 equals 4/3 pi times 3 times, what is my r? Well, I want to know r prime when r equals 2, so I'm going to plug in 2 times r prime, which is what I want to find. So I've gotten rid of everything except for the one variable that I want to solve for, which is r prime. And so then I'll let you guys work out the arithmetic there, but you will get r prime is equal to roughly, let me erase these and make my little swiggly, approximately 0.09 feet per minute. And units are super, super important on these problems. They are part of your answer. They are required. They are worth points. So remember your units. And there's always a way to tell what your units are going to be. And that's if you write it in this form. So if you wrote it as dr over dt equals approximately 0.09, you would know your units would be the units of r over the units of t. My units of r are feet. My units of t are minutes. So that's just kind of like a cheater way to know what your units are going to be if you choose to write it in the dr over dt way. All right, let's do another example. A 50-foot ladder is placed against a large building. The base of the ladder is resting on an oil spill, and it slips at a rate of 3 feet per minute. Find the rate of change of the height of the top of the ladder above the ground at the instant when the base of the ladder is 30 feet from the base of the building. So this one needs a picture. So let's draw a building, and then let's draw a nice little ladder right there. So there's my building, there's my ladder. Okay, the base of the ladder is on an oil spill, so there's a little oil spill right there. And it slips at a rate of 3 feet per minute. So I know that my ladder is moving this way at a rate of 3 feet per minute. Okay. And then find the rate of change at the height of the top of the ladder above the ground. So that's going to be this, and I'm going to label that as x. At the instant when the base of the ladder is 30 feet from the base of the building. So the instant when this right here is 30. Okay. So now I have all of my information. Oh, no, I don't. My ladder is 50 feet long. So I know this is 50 feet. Okay. So I know my ladder is 50 feet. The building height, we don't know, but we can find because there's a right triangle. That's not going to be a right triangle. Let me try again. We have a right triangle with the building and the ladder. We know that this is 50, this is 30. So we could say x squared plus 30 squared equals 50 squared, and then x is equal to 40. So we know that this is actually 40 feet. Our building is 40 feet. And now we have a complete picture. We have an absolutely complete picture. Let's write down what we're given and what we need to find. We are given, and given and find is kind of like, what are you given in terms of the rate, okay? And so the rate that we're given is that, I'm gonna call this y right here, this variable, dy over dt equals 3 feet per minute, right? So my units of y are like slipping out at 3 feet per second. Okay, so the rate of change of y, which is dy over dt, the rate of change of y with respect to time is equal to 3. Find the rate of change of the height. So that's going to be dx over dt in the way that my picture is labeled. Okay. And now I'm going to figure out which equation. This one's a little tricky, but it makes more sense if I look at my picture, right? If I look at my picture, I can see I have a right triangle. And I can think to myself, what equation do I know that relates sides of right triangles? Pythagorean theorem. So my equation is going to be x squared plus y squared is equal to 50 squared, right? Because my x, that rate of change is changing. The height of the ladder against the wall is changing. Y, that rate of change is changing. The ladder is slipping out. That hypotenuse length, that 50, that's not changing. The height of my ladder is not changing, okay? So my equation is going to be x squared plus y squared equals 50 squared. We're going to differentiate our equation with respect to t. So we're going to get x squared plus y squared equals 2,500. Okay, so then 2x times x prime, because I'm not a t, plus 2y times y prime, because y is not a t, is equal to 0. The derivative of a constant is 0. And then I'm going to plug in what I know, right? So I know 2 times x, which is 40, times x prime, which is what I'm trying to find, dx over dt, x prime. This is also y prime equals 3. Plus 2 times y, which I know is 30, times y prime, which I know is 3, is equal to 0. So I'm going to get 80 x prime plus 180 equals 0. 80 x prime equals negative 180. X prime is equal to negative 9/4. And then if I want to think about my units of x are going to be in feet over my units of time, which are going to be in minutes. So x prime equals negative 9/4 feet per minute. And if we look at the orientation of our picture, the ladder is sliding this way. So that makes sense that we have a negative rate because it's sliding in the negative direction. All right. Number 3, a stone is dropped in a pond. A stone dropped in a pond sends out a circular ripple whose radius increases at a constant rate of 4 feet per second. After 12 seconds, how rapidly is the area enclosed by the ripple increasing? So we have a stone dropped in a pond and it's causing a ripple, right? So this is going to be R, the area enclosed by the ripple, and it's going out at 4 feet per second. So that's kind of a ratchet picture, but as long as it makes sense to you, honestly, that's what matters. I know that the rate of change of the radius with respect to time is equal to 4, given. And I want to find the rate of change of the area, or dA over dt, at the moment when time is equal to 12 seconds. The equation is going to be my equation for the area of a circle, which is A equals pi r squared. And at this point, I'm going to leave it to you all to figure out the rest of this problem. Hopefully that setup made sense and you see where all of these things come from. And we will talk about the answer to this question in class and continue with practice problems during class time. So thank you for watching. I hope you learned something about related rates, and we will continue with this topic in class. So cheers.